Hello, and welcome to the MRC Weekend training presentation brought to you by New Jersey Search and Rescue and Captains Scott Fitterman and Jeff Berg. We'll be taking you through this presentation at a reasonable pace, and we hope that you get something valuable out of it. This is a brief agenda of what we'll be talking about today. We'll be going over some basic map and compass information, coordinate systems, some basic GPS use and discussion of datums, task roles on a task, radio protocols you need to know for when you're out in the field, and how to flag clues and edges of search areas. First, we're going to discuss maps. All right, to begin, pull out your copy of map 115. Examine it intimately. In the lower right, you'll notice a legend that has information like a scale so you can understand distance on the map in both miles and kilometers. You'll notice declination, as well as some information about how to read the various features of the map. Trails are in red, for example, roads are in black, and forested areas are in green.
If you got the newer version, it's actually map 150 now, the 2021 version, but you can use the 2017 115 until you get your copy.
You'll also notice that in the key is the datum that this map is in. For New Jersey Trail Conference maps, every map will use the UTM coordinate system, and it should be using NAD 83 as the datum. It's difficult to see on this map, but if you zoom in, you'll see small brown lines that represent the contour lines and elevation. And speaking of those contour lines, there's a couple things you need to know. The first is that there are index contours. These are thicker brown lines that show large increments, usually 700 feet, 800 feet, etc. There are intermediate contours which show a predetermined interval that helps you break down the large elevation changes between index contours on a map. That contour interval is also specified in the legend on a map.
In this example, the contour interval is 20 feet. So from 700, this would be 720, 740, 60, 80, and up to 800.
Contour lines on a map are used to represent different types of natural features you might encounter. Some of these are visible in the lower left-hand corner of your screen. You can see two peaks divided by a saddle. In the top one, a kind of pyramid shape. In the second, Scott, take it away.
We're going to skip the third one.
Yeah.
And you know, the next few are very similar, but you can tell, like on this fifth one here, that it's larger contour intervals between the lines means that it's a more gradual slope, just like this. And then when you get here, this flat part is equivalent to this flat part here. And same thing here, you go up, up, up at the top, go down to the saddle, and same thing over here, and you can see it represented here. So this picture, and we need a better picture, but this will do the job. We've got a few different terrain features here. One, you've got a hill, and you know this is a hill because this is the top of the hill because the circle is inclusive here. and it slowly goes up to the top, and then it slowly comes down. We'll skip right down to 4 because that's where my cursor is at. And we come down to a saddle where it flattens out, and then you notice it goes back up again. 7, that's not the greatest example of a spur. Here's a good example of a spur. So you're going along the ridge here, and this juts out as a spur and is coming down as well. And in between 2 spurs, you have a draw, a lot of times where water finds its way down the hill, and it's usually a good way to get down. What else we have? We have 3 we talked about. That's the ridge. A valley is a large lower section of terrain in between 2 higher areas, and this here is what they're depicting as the valley. We got a depression, which is number 5 over here. Different maps will represent it differently, but this is just an area that actually goes below the surface of everything in the valley here. And then you have the opposite, which is a fill, usually a man-made fill. Here's number 10, underneath train tracks, I guess.
Now that we've talked about maps, it's time to talk about compasses. For New Jersey Search and Rescue, you need to have a base plate compass with a mirror. A standard version of this you can see on the right. There's a sighting mirror that folds down on the top of it, a compass with a magnetic needle and orienting lines, an azimuth ring that can be rotated. Usually there's a sighting window and a clear base plate. All of your compasses should be able to be set for different declinations. We'll talk about those in a little bit. They should be liquid filled and preferably have a global needle. By global needle, what we mean is it will work in both the northern and southern hemispheres. Oftentimes, these are a little bit more expensive than a standard compass, and you could get by with a standard compass. It's very rare that New Jersey Search and Rescue is called out to South America. But there's another benefit to having a global needle, which is that the distance that it can flex to the base plate is greater, which means you have more latitude in how level you hold your hand when you're sighting.
That comes in quite handy when you're in rough terrain trying to follow an azimuth and your hand is jumping all over the place. So you don't have to worry too much about it being level. And these are really non-negotiable. The global, you can't get away without the global needle, but you do need that mirror because oftentimes we are taking azimuths in the field and targeting something in the distance, be it a tree or a rock or some other feature that we can recognize. And instead of having to watch our compass the whole time we go, we're able to tilt the mirror 45 degrees back towards the compass so we can see the compass in the mirror while we sight through one of the sighting holes above or below the mirror.
To help you out, if you haven't purchased a compass yet, these are 2 standard compasses we frequently see in use on the team. The first is the Sunto MC2G. It's the one that both Scott and I use, as well as about 90% of the team. The second is the Silver Ranger 2. It's a little cheaper, but also as good as the Sunto MC2G. And it comes in orange.
And I hate to say it, but the prices are outdated with, I guess, supply chain issues and so forth. Right now, the Sunto is going for 90 and the Silver Ranger 2 is going for 50. There's one other compass which is acceptable. That's the Brunton TrueSpec 20 or 21 it's called. There are some issues, but some people seem to like it. So that's an option you could look at as well.
And just for clarity, you should be looking for a compass like this instead of something like a lensatic compass. Okay, let's talk about how to hold your compass. If you haven't gotten your compass out to look at it yet, get it out now. Put it in your hand. If your hand is flat with your fingertips pointing away from you and your palm up, the compass will go on top of your hand as if you're serving it at a fine dinner. You'll tilt the top of the compass with the sighting mirror towards you so that you can sight through the sighting ring on your compass and still see the needle of the compass in the mirror. As we mentioned before, make sure to keep the compass flat. There's some leeway you have, but not a lot. And if you tilt too far up or too far down, the needle on the compass will pull down and contact the base of the compass, which will stop it from moving smoothly, which you need in order to be able to get a proper reading from your compass. Primarily, there are two things you're going to have to be able to do with your compass. The first one is to follow a sighted destination and to identify the azimuth from that destination. In order to do this, you hold your compass in the palm of your hand, you line up the feature through the sighting window, and then you rotate the bezel of your compass until the red section of your needle is inside the shed, as we call it, a red indicator, usually with an arrow on the end. And then the azimuth that you'll need to follow is located at the white line in the front of your compass. Where that intersects is the proper azimuth. The second thing that you'll need to do is follow an azimuth. To do that, you're essentially doing the first thing in reverse. You use your map to determine the azimuth that you'll need to follow, and then you spin your bezel to line the azimuth up with the white line at the top of your compass. That's going to be your direction of travel. Then you hold your compass in your hand, looking through your sighting window, and rotate your body until red is again in the shed. Landmarks that you see through your sighting window at that point are along the proper azimuth, and you should walk towards them if you want to follow the proper direction of travel.
So for example, if you determined from your map that you needed to go 93 degrees to get where you're going, you would take your compass out and you would spin the bezel until 93 degrees was lined up with the direction of travel arrow right below your mirror in the center. And once it's lined up, you spin yourself around until red is in the shed. Make sure that your arm is outstretched as far as you can go and that you're keeping it level. And also make sure there's no magnetism in the area or on you that might affect it.
That's a great point, and it brings us to magnetism. Many things that you encounter in the field will be magnetic. The radio in your chest harness, for example, your GPS, your watch. All of these things can be magnetic, and they'll pull your compass off true. In addition to things that you wear on your person, you might also encounter magnetic fields in the ground itself. In the areas that we're hiking, many iron deposits exist. And if you're standing on top of one of those iron deposits, you might get some odd readings on your compass, either things that seem like they're obviously incorrect, or a wavering needle that indicates a fluctuating magnetic field. In the event you encounter one of these, the best thing to do is to take a reading as best you can, and then move a few steps off of where you are and take another reading and see if it matches. If that resolves any type of wavering needle issues, perfect. If you're still getting a wavering needle, walk a little farther and try it again. At that point, you'll know whether the issue is a large iron deposit underground, or, for example, just an issue with your compass itself.
a lot of times you'll encounter this in really rocky terrain. And another great method is you could go off in the direction that it's telling you to go to. And then after you get, 25, 50 feet away, turn around and do a reverse azimuth back to where you started and see if it matches up now that you're no longer on those rocks. And if it doesn't, you know that you had some magnetism affecting you.
Yes. Another thing to keep in mind is that in addition to electromagnetic fields that might be generated from under the ground, there also might be electromagnetic fields generated above you. For example, if you're standing underneath power lines, you might get an improper reading. You have to be pretty close to them, though, for that to happen.
I don't know if you mentioned it, Jeff, but some big ones that have caught some of us off guard are magnets in gloves that flip back and they're held with a magnet. Also pace counters. You got to make sure that even the plastic ones, they have metal inside that are magnetic, that you're using that in the other hand.
So now that we've talked a little bit about compasses, let's talk about declination. Declination simply is the difference between magnetic north, which your compass points to, and true north, which is the actual direction of north. Declination changes depending on where you are in the world. In New Jersey, we're usually right around 13 degrees west declination. If you don't have a compass that you can adjust declination on, then in your head, you need to be computing declination. So if you're going map to field, you would need to add 13 degrees. If you're going field to map, you would need to subtract 13 degrees. All of the compasses that we recommended, though, allow you to adjust declination, which is done using the little key that comes with your compass, usually a piece of flat stamped metal on your lanyard, and a small screw that's on the back of the compass, which allows you to adjust at 13 degrees north or 13 degrees, I'm sorry, 13 degrees west or 13 degrees east. Here's an illustration of that. Every map points to true north, or as Scott and I call it, geographic north. This is the direction to the North Pole of the world. Your compass, however, the needle will point towards magnetic north. That is the strongest magnetic field that it can interact with at any given point in time. In order to fool your compass into giving you proper azimuths to match with your map, you need to adjust your declination. Once you adjust your declination to 13 degrees, if you're, say, where we are, at that point, the compass heading will match any azimuth to true north. Now that we've talked about maps and compasses, let's talk about map and compass. One of the things that you'll need to do in the field and also demonstrate to us over MRC weekend is your ability to orient a map both with a compass and with terrain. First, let's talk about orienting a map with a compass. In order to do this, turn your bezel so that north is lined up with your direction of travel. And then place your compass on your map with the grid lines between the map and the grid lines on your compass lined up. Then turn your body until red is in the shed, and now you're facing the proper azimuth.
I don't think we have a slide on orienting a map to terrain, but that's pretty self-explanatory. You're going to be expected to be able to do this on your way to wherever you're asked to do this. Keep an eye out for different features, whether they be streams, elevation changes, trails, any other features that you come across. And then when you look at your map, and it's something that you should practice while you're hiking in the woods all the time. You should always be aware of your surroundings. you should be able to find those features on the map and pinpoint exactly where you are.
All right. So also, when navigating in the woods, one of the things that you need to be able to tell is a safety bearing. The safety bearing is essentially an azimuth that you can travel from anywhere on the map or that you're going to be that will take you to a feature you can identify. The map we're looking at here is a map of Ringwood State Park. And the safety bearing you can see on this map is almost directly due west because it will take you to the White Trail or a road the entire length of this map.
So let's say you started from here, or you started from here, or you started from here, but you knew that you were going in an easterly direction. You were going to be somewhere in this area. You knew that no matter where you ended up within the next 12 hours, you could go west and hit a perpendicular feature that could then get you to safety.
One of the other things that you'll need to be able to demonstrate in the field is your ability to plot azimuths or bearings on a map. In order to do this, you put your compass on your map, oriented in roughly the direction of travel that you want to draw a bearing in. Then you turn the bezel so that north is pointed roughly north, and you use the base plate of your compass to line up an exact line of travel from your origin point to your destination. Then turn your bezel so that the compass orientation lines match up to your map grid lines and take a reading at your direction of travel. That is the azimuth that you want. One important thing to remember when you do this, though, is make sure that north on your compass matches north on your map. It's very easy to accidentally get the opposite azimuth if north is pointing south, or if your direction of travel on your compass is oriented in the incorrect direction. We've gone over the basics of what you would need in order to orient yourself using a map and compass in terrain. However, if you want a more in-depth look at this, we recommend these two books. Be Expert with Map and Compass, and also The Essential Wilderness Navigator. Both of them give wonderful tips and in-depth information about how to properly navigate using your compass while in the field and how to use it with a map. Now that we've talked about how to use a map and compass, let's talk a little bit about how you either indicate where you are or understand positions on a map, which is to say, let's talk about coordinate systems. Probably the coordinate system that you're most familiar with is latitude and longitude. We don't use it so much for New Jersey search and rescue for reasons that we'll explain in a second, but latitude and longitude is roughly measured using your angle north or south relative to the equator and your angle east and west relative to the prime meridian. Assuming that the Earth is a sphere, latitude and longitude divides the world up into 360 degrees, either horizontally or vertically. And each degree is separated into 60 minutes, and each of those minutes is separated into 60 seconds. There are three main flavors of latitude and longitude. We have these at the bottom of this slide. The first is degrees, minutes, seconds. You can see an example below this, and you would read it as 41 degrees, 6 minutes, 58.8 seconds north, 74 degrees, 6 minutes, and 19 seconds west. Underneath this is degrees, decimal, minutes. The coordinate underneath it is the same, but you would read it slightly different. This would be 41 degrees, 6.97920 minutes north, 74 degrees, 6.31620 minutes west. They're the same coordinates as above, just expressed slightly differently. And then the last one is decimal degrees. I'll spare you having me read another coordinate to you, but you can see that this is the same as above, also just expressed slightly differently. Primarily, the two flavors you'll encounter most often are degrees, minutes, seconds. These are very common on maps, for example, especially old survey maps, or decimal degrees. This is what's displayed in, say, Google Maps. And this is what frequently we would be given if there were people in the field who got their position from Google Maps and relate it to us, and we had to respond. Another very common set of coordinate systems are the Universal Transverse Mercator and US National Grid. These two systems are very closely related. But first, let's talk about UTM a little bit. This is what all of your trail maps will be on here in New Jersey and in many places in the world. It is very useful for maps because it provides very low distortion, which is to say that between any two grid squares is the same amount of space at any map you look at, but between two lines of latitude or longitude, as you get closer to the North Pole or South Pole, the distance between those lines would get smaller. UTM divides the Earth into roughly 60 zones. And at its base, the smallest unit inside of a UTM grid is 1 meter, which makes it very useful for doing measurements or calculations in the field. On a map, each grid square is usually about 1 kilometer, especially on the trail conference maps that we use. The format looks like what you see here. 18T 0575116 by 4552063. US National Grid is closely related to this. It's very similar to UTM, and it's even kind of based on it, but it further breaks down locations into a smaller grid. For example, the same coordinate that we had above in UTM is visible here as 18T WL 75116 by 52063. You'll notice that the 5 by 5 numbers at the end of the US National Grid are the same as the last 5 digits in the easting and northings in the UTM coordinates. And that's because it's the same coordinate. The only difference is that it's broken down into a further grid, WL, which is roughly accounts for, well, never mind. It breaks down into a further distance called WL.
You will notice that these two UTM coordinates are slightly different in terms of the number of digits. This one is 7 and 7, and this one is 6 and 7. If you're ever given these and there are no spaces, you'll know that this one needs a leading 0. The first set of numbers always needs that 7th leading 0 if it's not there.
This is a UTM zone designation map, and in it, you can see all of the zones. Frequently, in New Jersey, we're in 18T, which you can see by finding the 18th column and the T row right there. Almost everywhere in New Jersey and almost every search we respond to will be within this UTM zone reference. Let's illustrate one of the really cool things about UTM parameters. Here, you'll see a satellite image of our headquarters. And the coordinates 18T 568187 by 4547653. This gives us a point 1 meter by 1 meter located directly in the center of our headquarters. However, if we remove one digit from that, we now have an area roughly 10 meters by 10 meters that we've defined using coordinates. We just say it's 18T 56818 by 454765. If we remove another digit, we now have an area that is 100 meters by 100 meters, designated using only 4 digits by 4 digits, or 4 digits by 5 digits.
Although there would be a leading 0. So this would actually be 0000 to 9999, including this entire box. And we do the same thing with US National Grid.
Correct. And the reason why our headquarters isn't centered in the middle of that is that the area is defined as 100 meters by 100 meters with reference to the UTM grid system, not by what's in the center. Now let's practice a little bit. Pull out map 150 again and find the distance between Matty Price Hill and headquarters. Use this by using the scale on your map or using a UTM grid reader and making an estimate. Also, find the coordinates for the top of Matty Price Hill. You can do this by making an estimate, breaking up the 1 kilometer UTM grid that it's inside of into sections, into halves, into quarters, into tenths, both horizontally and vertically. Once you've done that, find the location of the top of Matty Price Hill within that square and send us an email if you have our email addresses of what those coordinates are.
Oftentimes, people have a difficult time matching up the numbers in the coordinates they're given with the coordinates on the actual map on the sides. So something that I do that helps me is that the last 3 digits, and again, we'll usually be using US National Grid, which is just the last 5 digits of the first set and the last 5 digits of the second set. So the last 3 digits of each set, 832 and 683, are all within a box. So you won't see those numbers down here or over here. That's figuring out exactly where in the box it is. It's the first 2 of the 5, 06 and 44, that tell you which box it is. So 06, as we're doing easting, we come this way, 06, 07. So we know it's bigger than 06, so it's going to be to the right of this line. And north-south, it's 44. So it's 44 plus some, 683. So it's going to be above the 44 as we get to the 45. So it's going to be within this box. Then we look at the 832. We're moving over to the right about a little more than 8/10 of the way, which they've done here. And then with the 683, we go up. This would be about 500, and it goes up almost 7/10 total to this spot here. You can get the exact location with a grid reader, or as Jeff was talking about before, making your own grid reader on a piece of paper by separating it into tenths. But most of the time, you could just do an estimate and say about 7/10. Well, actually, you'd start this way: about 8/10 to the east and about 7/10 to the north, and get this area.
Now that we've talked about map and compass and map and compass, let's talk about something that means you'll never have to use them again: GPS. There are many, many different flavors of GPS devices out there. They could be handheld ones, they could be apps that are on your phone, and we'll talk about them in a second. But regardless of what you use, there are a couple basic things you need to know, and it is your responsibility to know how to use your equipment. The first thing you need to know is how to change your coordinate system and format. This is something you'll need to demonstrate to us over the course of MRC weekend. You'll also need to know how to change your datum. Another thing you'll need to demonstrate to us. You'll need to know how to find your current coordinates when you're looking at your GPS screen, and how to create and name a waypoint. You'll also need to know how to start, clear, record, save, do basically anything with a track. And then lastly, you'll need to know how to give your track to somebody else. This could be over email, it could be directly uploading it to a computer, but you'll need to know for your specific GPS device how to do that. And if you need to upload it directly to a computer, it's your responsibility to make sure you have a USB to whatever flavor of connector goes on your GPS device cable. Now, let's talk a little bit about datums. Essentially, datums represent a way to put the coordinate system into actual places on the globe, reference points that we use to overlay coordinate systems. There are a couple main datums that you'll probably see. The earliest one is NAD 27. It was the first well-used North American datum, and it was created in 1927. It was good for the time, but technology has improved significantly since then that allow us to be a lot more accurate. And NAD 27, while it might exist on very old maps, is not used currently on modern maps. Instead, you'll probably see either NAD 83 or WGS 84. Both of these are very similar. NAD 83 was created as an update to NAD 27 in the year 1983, as the 2 digits on the end kind of indicate. And it used things like satellite geodesy and remote sensing to better approximate the shape of the Earth. WGS 84 was created 1 year later, and it represents a global system. It's very, very, very similar to NAD 83, and they're often used interchangeably. So on some GPS devices, you'll see one or the other, but not both. Now, NAD 83 and WGS 84 differ substantially by NAD 27, often by tens of meters, but it depends on your location. So for example, the same set of coordinates represented in the real world would be 95 meters apart in Seattle between NAD 83 and NAD 27, and in Miami, roughly 50 meters. It is vitally important that before you go out into the field or before you communicate coordinate systems to anybody, you make sure that your GPS device is set to the correct datum based on the map that you are using. If you're given an NAD 27 map, it needs to be set in NAD 27. If you're given a US National Grid map, it needs to be set in NAD 83, which is standardized on US National Grid is standardized on NAD 83, and so it has to be set for that. This information should be available to you at the on the whiteboard in the staging area. If it's not, and all up there are coordinates, plug those coordinates into your GPS device and see if it gives you the location that you're at. If it doesn't, this might mean your datum is off.
This is important because oftentimes on drills, we might practice switching between NAD 27, NAD 83, WGS 84, so that we know how to do it when we encounter a map, an old map that, say, somebody out there was using to find mines or whatever it is. And then we go home, and then the next day we have a search and it's still set to NAD 27. And that would put us in a totally different location for the coordinates we're given than if we had the correct datum, NAD 83, with the map that we're using that day. So it's important to always check, as Jeff said, the whiteboard at staging and to know how to change your datum on your GPS device.
There are a couple other things that you're going to need to be familiar with on your GPS device. The first is the waypoint button. Every GPS device should have a way to create a waypoint. Oftentimes, it's a dedicated button. Sometimes you have to go into a different menu, but you need to know how you create that. On most dedicated GPS devices, you'll have a button. And when you press that button, it will drop a waypoint at your current location. The other thing you need to know in your settings on your GPS device, frequently, it gives you the option to choose north up or heading up. North up would be kind of like a map, where north is always at the top of your map. Heading up would be similar to a GPS device that you use for driving, where the azimuth at the top of the device changes depending on the direction that you're facing. Do everyone a favor, and when you're out in the field for New Jersey Search and Rescue, use north up. It's much easier to use when hiking, and it's much easier to help orient yourself with a map. Many GPS devices also involve more than just GPS satellites. For example, GLONASS, which is a Russian positioning system similar to the GPS system that we use in the US. Turning the setting on can give you better accuracy or a quicker fix. Turning it off will save battery life. So it's kind of a trade-off. Usually the battery consumption on this is minimal. So unless you're running very low on batteries, it makes sense to turn this on if you have the option to use it. EGNOS is similar to GLONASS, but it's European and not Russian. In addition to both of those, which are satellite systems, there's something called the Wide Area Augmentation System. And this, just like a GPS device communicates with satellites, communicates with stations on the ground to give you a more accurate GPS reading. Turning this on will increase accuracy, but again, come at the cost of battery life. Also, many GPS devices have a routing method. This handles how a GPS will produce a route to a destination. For example, if you enter headquarters in your GPS as you're driving to a drill, the route that it takes you on roads is the same type of route this could create. Most GPS devices do not have the ability to route along trails. And because of that, for off-road travel, you should have this set to direct routing, which will take you on the shortest route, usually a line between 2 points. Otherwise, it may try to route you along a road, it might not realize that there are trails that are there, and you might end up taking a much longer route or an incorrect route to get to a location.
All right, that brings us to the end of our discussion on navigation, maps, compasses, GPS. We'll talk a little bit about task roles. There is no defined number of members on a task. So these are the roles, although sometimes people might hold more than one role. You will always have a task leader, and the task leader will designate the other roles. The task leader is going to get a briefing from command, either at a drill or at a search, as to the objectives for their task. The task leader will assign a navigator who will be in charge of figuring out the best route to search or to wherever their destination is. You'll have somebody on comms. Comms could be radio, it could be Zello, which is a push-to-talk app on our phones. It could be cell phone communication, but that person is in charge of relaying information back to command and receiving communications from command. You'll have a medic. which is not a medical designation. It's just the person in charge of medical on the task, usually the person with the highest level of medical training. And that is the person that will immediately go to the patient once a find is made, and it'll also be the person who deals with any medical issues that members on the task have. You have a scribe who is going to record everything that goes on during the task, the times that certain things happen, the clues that they come across, the communications that are made, everything is put down. The scribe does quite a bit of work when a find is made, and all of the medical information has to be recorded and then relayed through comms back to command. And then you have a safety officer. Safety officer shouldn't be involved in anything else. They should be watching over everything going on and making sure that that the conditions are safe for what you're doing and that everyone is behaving in a safe manner. Oftentimes, the task leader will also be comms and the safety officer. The other roles are usually separate people.
Yes. A couple other points that are worth mentioning. Navigators also are responsible for plotting a route from the subject to a safe location for evacuation after a find is made, and should start doing this immediately when a subject is found. Also, there are some things that can never be combined. For example, task leader and medic, or task leader and scribe, because the task leader has responsibilities at the point that a find is being made. And if they have to be writing down or doing an assessment, they can't be doing those responsibilities also.
Radio communication. If you haven't used radios before, there's a few etiquette rules that we need to go over. The first is you don't want to be stepping on other people's radio communication. So you want to wait for traffic to clear, radio traffic to clear, before initiating your transmissions. Once somebody else is done speaking, then you can start. Before you even start though, you want to think about what you want to say. You don't want to be stumbling as you're in the middle of your communication. You want to hold down the button for at least 1 second before you start talking, because oftentimes it takes a second before it can pick up your voice. You want to be clear, simple, and brief. There are a lot of other people in the field that need to make communications as well. So you want to get your communication over to command and then sign off as quickly as possible. When on NJSAR, when we initiate communications, we always say who we are calling and then who it's from. For example, as you see there, comms from task 3. Other organizations might flip that around, but you need to remember this is the way that we do it. Always who you are calling and then who it's from. You want to speak slowly and clearly and confidently. The more times they need to ask you to repeat, you delay other people's communications, so you want to get it right from the get-go. We only use plain English. We do not use 10 codes like 10.4, 10.10, or any other 10 codes or other codes. In order to communicate numbers such as coordinates, you want to say them in small chunks, either 2 or 3 at a time, such as 5, 6, 4, 3, 7, 3, 9. If you say them all in a row, 4, 6, 5, 3, 7, 3, 9, it's going to be much more difficult to take them down on the other side. You want to learn the phonetic alphabet. Oftentimes it's hard to tell one letter from another when you're communicating over the radio. So instead of saying the letter A, you would say alpha. Instead of B, you'd say bravo. And it just makes it a little clearer when you're trying to communicate coordinates like 18T, 18 Tango is better. We want to use our J numbers. Every member on our team has a J number so that we keep our names off of the radio. Our radio channel is a public channel. Anybody can be listening. So not only that, we want to keep all personal and sensitive information from the communication. If you need to convey something personal about a subject, then you want to call on the cell phone instead. In order to confirm, especially with coordinates, but with all instructions, that the person on the other side received them correctly, they should repeat it back to you. And when you are given instructions or coordinates, you should read them back and confirm that they are correct. Small words like yes and no are sometimes difficult to understand. So we use words such as affirmative and negative instead of yes and no. We also use say again when we want somebody to repeat something, and we say received instead of 10-4 or any 10 codes to let them know that you have received the communication.
All right, we've covered almost all of the basics, and the last thing to talk about is flagging. First, make sure in your pack you have a roll of flagging tape as well as a Sharpie so that you could write on that flagging tape. You're going to use this flagging tape in a variety of different areas. You might use it to flag clues. You might use it to flag the corners of a grid search area. You might use it to flag an evacuation route. Any flag you put up, except maybe for the flags that you put on an evacuation route, should have some basic things written on it. The first is the date and time that you're placing the flag. The second is the location that you're placing it at, so that if you put a flag up and then later on somebody moves it, we'd have a way to track that. And also your task number that you're part of as you put the flag, whether it's task 1, task 2, evac task 3, whatever it is, make sure you indicate who you are when you're putting it up. When you're placing flagging around clues, you're not going to place a single flag. Instead, you're going to want to place flagging tape in a square with the clue at the center. The square should be visible and not on the ground if possible. So around 4 trees with the clue in the center of them, for example, would be pretty good. But it should be visible and it should not be in a place where it will be stepped on. If you're ever called on to flag corners of grid search areas, for those, you flag them with 3 flags each. The reason for this is that oftentimes for large search areas, you might flag a bump line or your stop line, or you might flag along a route. But those will never be 3 flags on the same thing. So for corners of search areas, 3 flags. For anything else, 1 flag. Except for clues that are not really a flag at all, it's a square around them.
Good luck at MRC.
Yes, enjoy. Can't wait to see you guys there, and it'll be a blast.
And feel free to email Jeff or myself or both of us with any questions you have from this recording.